sorry for the confusion, but I haven't done like any kind of like EEG source reconstruction of this since years now. But I have to know and see how we can do that. So I'm extremely pleased to welcome Professor Dirk Oswald, who you know already quite a bit, and as promised, so he's going to talk to you about like this very exciting topic of combining EEG with fMRI. Yeah? And you will see us hopefully like in a better situation on my side at least than tomorrow. Yeah. So enjoy the day.
I never know why he stays for this. It's every year this way. Yes, so simultaneous EEG-fMRI. So it still seems to be a topic. It still seems to be a topic. So I was in September. I was at Computational Cognitive Neuroscience in Philadelphia, and there was a session. What was it on integrating models and data or whatever. And there was an introductory. Introductory talk, and that mentioned that EEG-fMRI, so combining EEG and fMRI, is an exciting branch, maybe for doing more computational cognitive neuroscience. I actually have been out of EEG-fMRI, so combining that for almost 8 years now. Or no, that's not quite true because I worked on papers afterwards, maybe 6 years now. And my personal feeling is a little bit that not that much is happening there. But so maybe I'm a little bit biased also, and I'm not seeing certain things that people might find exciting now. So what's the plan? So the plan is to talk first about the motivation for doing EEG-fMRI, so combining EEG and fMRI measurements, and then talking about data acquisition aspects, because as you know, MRI happens in a magnetic resonance imaging environment, and EEG uses electricity and metal usually, and these two might not go that good together. And then in the last part, I will talk about how to make sense of the data. And I think so. The whole story essentially of this talk is, and also the way I see EEG-fMRI combination right now, is that the motivation on a superficial level at least is clear. Data acquisition is fairly simple because one can essentially buy all of it. One can also clean the data well, but then it's not clear what to do with the data. So people have done certain things. I also have done certain things, but a real integrative modeling framework that somehow does a nice data fusion and helps us with cognitive neuroscience has not yet been developed. So that's room for future research. So that's basically the short story of the whole thing. So the motivation, I guess, is relatively clear to you now, because you just essentially reviewed everything that you learned in the first year in the last 2 weeks again, because you learned about fMRI and EEG again. And so you know very well that EEG refers to electrical activity that is measured at scalp electrodes. You know, and you learned about the detailed biological, semi-detailed biological model that underlies EEG as synchronized postsynaptic activity. And importantly, you know that that activity changes in the EEG can be observed at a millisecond scale. So you memorized some event-related potentials. So you know that. And you also know that it's not enough if a single neuron is active to see something in the EEG, but it needs to be a larger patch of cortical surface. You also know, it's somehow strange that you all sit behind computers, but that's fine. Maybe go a little bit down with your head, then we don't really see each other at all. So the EEG, you also know that the EEG detects widespread cortical activity, that deep structures, for example, basal ganglia activity is not really that observable, which is still a good motivation for actually doing MRI if one wants to look at deep structures. Then that what you see in the EEG might come from somewhere else. So you have this EEG volume conduction, so localization is relatively tricky. And of course, you also learned about the EEG forward and inverse problems, so that the whole thing to get from a cortical source to the EEG and back is not necessarily simple, and also requires some modeling assumptions. So, short story, of course, EEG has good temporal resolution, but the spatial resolution is not that clear. fMRI, you know by now that it's driven by the Bolt signal, that it's metabolic demand, so it's not direct neural activity as opposed to the EEG. You remember how the Bolt signal is created, and you also know that there is a temporal delay between stimulus induction and the observation of the Bolt signal. So this is kind of an overview picture of what's going on in terms of EEG-fMRI neurophysiology. So you have a stimulus or some resting state activity. You have neural activity, which you can, if it's synchronized and over some large patch, you can observe on the EEG, and then upon the neurovascular coupling stage, you can observe hemodynamic responses and Bolt responses using fMRI, however, with some temporal delay. So you know all of that. This, I think, is the first figure that I also used in the original introductory courses. So the idea is then, of course, that if you look at the spatial temporal resolution of different neuroimaging methods, that there is some complementarity. So, for example, if you look at patch clamp recording, you had a very small spatial scale. If you're looking at scalp ERPs with EEG, you had a relatively coarse spatial scale, and but still at a high temporal scale. And with fMRI, you might go a little bit more to a higher spatial resolution, but you also have some temporal delays. So this is kind of the intuitive and very intuitive motivation. So if we can measure neural signals here and neural signals here, if we then combine our measurements, then something awesome will happen and we will have great results, highly significant and awesome paper. So that's kind of the idea or the initial motivation. The problem is that it's not really clear what it actually means then to combine this. So because in a way you can already combine EEG and fMRI data by looking at EEG papers and looking at fMRI papers, and then you find, okay, these areas are activated, it happens at these time points, for example, for a checkerboard and stimulus, as you all know, and then you can say, okay, so the temporal scale, it seems to be that there's some processing around 100 milliseconds. On a spatial scale, it seems to happen in occipital areas. So combine the stuff. So the question is then, what in addition to that, does one want to gain by EEG-fMRI combination, specifically from a cognitive neuroscience perspective? So this is again just what I said. So fMRI, hemodynamic activity, millimeter spatial resolution, temporal resolution, limited seconds, EEG, complementary to that. So what was then the initial application of EEG-fMRI? And that is actually interesting because it's not was not already, driven by the idea of doing cognitive neuroscience at high spatial temporal resolution, but with something in mind that is actually more sensible, namely to increase the spatial position of epileptic foci. So the problem with epilepsy as opposed to cognitive neuroscience research is that in epilepsy the electrical and neural events are internally generated, right? So it's endogenous activity, and you don't have control over that. So if you want to do some spatial localization using fMRI of these activities, you don't have a temporal onset just from an experiment like you had in the fMRI data analysis, but you actually, the temporal onset of activity is endogenously generated by the patient suffering from epilepsy. And then, of course, the simultaneous acquisition of these two modalities makes sense because otherwise you would not know when to look for activity that is related to the onset of an epileptic discharge if you don't record the EEG at the same time. So this is a clear and strong motivation for simultaneously acquiring EEG-fMRI data. In cognitive neuroscience, for doing simultaneous EEG-fMRI, it's a little bit less clear. So one thing that one can talk about is that getting the signal at the same time allows for a more complete view of the brain's response to a given stimulation, because you look at how it's mapped both, if you assume that there's one neural activity, how it's mapped both into both signal domains. Maybe some precise spatial temporal characterization is possible, whatever that means. And so these two things that I just mentioned are, again, more on kind of an intuitive level that need to actually be implemented into formal models to actually be achieved. What is true in terms of simultaneous acquisition, if you think about learning effects or fatigue effects, so if you want to have want to look at EEG activity and fMRI activity in a learning experiment where people, learn something that they can only learn once, then of course you cannot do first an EEG experiment with some subject and then an fMRI experiment in other subjects. What are you actually typing? Are you writing? Oh, no. And you don't have to, you will get the slides, you don't have to type the slides. So if you do a learning experiment, then it might actually make sense to do it simultaneously because the participant can only go through this learning once. So that's kind of a clearer premise for cognitive neuroscience than the just the idea that it's somehow you get a more awesome result. Good. So that's kind of the motivation where this is coming from. So essentially, with good motivation in a clinical context, epilepsy mapping, and some, of course, intuitive feeling that this, from a cognitive neuroscience perspective, that this would be great to monitor EEG and fMRI together because they are kind of complementary, but not really, it's not really clear what that means. But with this kind of motivation, one can, of course, go into saying, okay, let's do an experiment and let's require EEG and fMRI data at the same time. Then we have it, and then we see what we will do with the data, maybe later. So the next topic then would be data acquisition, so how to actually do that. So, of course, it requires the EEG equipment to be NR compatible. So, if you go into the scanner, you know that you have to be metal, so you shouldn't have any metal with you. And if your EEG system has a lot of ferromagnetic metals in it, then it might not be a good idea to bring this into the scanner room. And also, you don't want to, of course, endanger the participant in the sense that, as you know, there are radio frequency fields applied similar to a microwave. You don't want to heat up, which actually sometimes happens, heat up the electrodes that are on a participant's head in an EEG system. So this, of course, needs to be taken care of. However, and this will be the next thing that's also coming up, one can buy systems that actually fulfill these criteria. So not like in the early 90s where you had to build your own stuff. And these days you can buy it, and the Max Planck has like 2 or 3 of these systems sitting in their, mostly sitting in their shelves and getting dusted. At least when I was there, they had awesome systems when we were using them. But we also have these systems and don't use them that much. Then the other thing is that there are interactions between the stuff that's happening from the MRI side and the stuff that's happening in the EEG leads. So as always, when you have magnetic fields, this induces electrical currents, and you still, with the EEG, also in an MRI context, you measure an electrical signal, and you have wires or leads, and in these, the MR gradients induce currents, which actually mask quite strongly the biological EEG signal. So you induce, with the MR machine, you induce currents up to 10 millivolt, or potential. This is not a current, it's a potential fluctuation, and which of course is accompanied by a current. And for the physiological voltages, not current, are at a much smaller microvolt range. So you mask things. Yeah?
So, for example, this high magnetic field induces some currents in the hardware of the EEG, but does it also apply some induction currents inside the brain, so some kind of artificial signal?
That's a good question. This is what you should ask the fMRI people. Yes, I would think so. I mean, you can induce, of course, you can induce peripheral stimulation in MRI experiments. That depends a lot on the actual gradient sequence. So I only had, when I did MRI, I never had anything induced for EPI sequences, so for the standard bolt sequences, which are also used here. But I remember that at some point I took part in a DTI study, and there really my so the peripheral nerves were twitching. So yes, it can. I think for in terms of the gradients that are used for EPI, at least I never experienced any twitches, which would be kind of a strong manifestation of that. Whether it's happening at a lower level, one doesn't know, but then, as I will show you later, one can of course record EEG activity in the scanner and look at it, and then look whether it's drastically changed, so whether the whole brain works different under this. And this, as I will also show you, does not seem to be the case. So yes, I would think that there is some induction, but it seems to be quite small, and of course it's also not, I don't know how inductive, if you think that you have kind of a a biological conductor compared to a wire conductor, I would assume that this takes much stronger magnetic fields to induce something in a biological system than in a wire that is optimized for this. So, but yeah, it's definitely a good thought. So this, given that there are these gradient artifacts, not only those, but they are there, one works in the dynamic range that is different from the dynamic range that is used or that is involved in standard EEG, because the induced voltages are much larger. So one definitely needs to make sure that in terms of, if you remember our stuff on sampling the EEG, both in time and in terms of the voltages, one needs to make sure that one doesn't saturate the system, so that one still can acquire meaningful time-varying signals. And because the MR gradients are quite fast, I mean, they're really fast, and one needs to describe them well in order to then filter them out, essentially. One usually uses a much higher, so by an order of magnitude higher sampling frequency. So that the usual would be 512 Hertz. And for EEG-fMRI, one uses a 5,000 Hertz sampling frequency, which also makes the data sets much larger. And then for the signal transfer, and this is shown here. So here are the electrodes. These are the electrode leads. So these little wires, which one can kind of safely take into the scanner, and then it goes to the amplifier. So this should ideally be fairly short, this distance between the electrodes and the amplifier, but then the signal from the amplifier is transported out of the MR room using optical cables and not electrical cables, because they are quite long and they need to, depending on how the setup is, go quite a long way through the MR setup. And as I said, one can buy these systems. So here you see participants in a Philips scanner with electrodes and electrodes lead on them, and then going to the amplifier, which is at the end, other end of the bore. They are not maybe in there.
How much more expensive is this amplifier system compared to the other ones?
I don't know. I actually don't know.
Is
I
it
think
about
it's.
the same? Is it twice?
I think it's about 5 times. That's my guess, but it's not that expensive.
Maybe a question. So how does this work with the electrodes? They're also made of metal, right? Like I have this maybe naive idea that you can't like have any metal in there at all, or go crazy. But maybe that's just.
Yeah, no. So so there are different kinds of metals. So some metals that are drawn to the scanner, I think they're called ferromagnetic, I guess. Those are like iron, and then there are metals that are not ferromagnetic. And these silver chloride electrodes, they are actually not ferromagnetic, so they don't get drawn anywhere. So the reason why when it's always said don't take any metal in there is because it's not clear, the metal that you have, what kind of mixture of metal that actually is. So, but there are metals which can be taken into the scanner. I mean, the scanner itself has quite a lot of metal. So you know that, think about when you were a kid and you had a magnet. Everybody had a magnet. You still have magnets on your refrigerator, and some things you can stick to them, and other things, although they look like metal, they don't stick. And this is why for example, these electrode leads, they don't stick to the scanner. But for example, my glasses, they were always drawn a little bit to different kind of metal. Good. Yeah, and the commercial solutions that are available are actually quite good. So with the brain product system, it was fairly uncomplicated to record the EEG data that you also had at your disposal, but I think nobody looked at. So one thing that surprised me when doing these experiments is that actually, because this takes quite a long time, so as you know, we did these experiments in the way that we first did outside EEG. So we prepared the EEG, then recorded outside EEG, and then we took participants into the scanner, and then they were in the scanner for another hour. So the whole thing took quite long, and I was always worried that at one point the electrodes essentially fall off and so on, but the EEG signal over time with this system actually stays very constant and actually gets a little bit better over time. So it's, I think if you want to record EEG-fMRI data and you're happy to read the manual and stick to the manual, then it's not a big problem experimentally. The question is just what you want to do with the data afterwards. That's the big problem. It's also not, so the recording is not that much of a problem, or it's actually not a problem. What is also not a problem is actually these artifacts that are induced. And one can think about artifacts in both directions. So on the one hand, the MRI generates artifacts in the EEG. Otherwise, the other way around, of course, the EEG might also induce artifacts in the MRI. And the first of those, so artifacts in EEG due to the MRI environment, they are actually quite significant. So there is what is known as the image acquisition artifact, or as I also called it earlier, the gradient artifact. And then there's another artifact which is known as the pulse artifact or ballistocardiogram artifact. And they need to be corrected. So here you see kind of standard EEG as you recorded it this morning, and here you see EEG recorded when the scanner is on, so while the scanner is running, and what you see here is essentially the strong gradient artifact. The other way around, in terms of what kind of artifacts are induced in MRI due to EEG equipment, there is a bit of a interaction still with the silver electrodes, in that they change the magnetic, the Bézier field a little bit, which doesn't lead to the fact that they somehow are attached to the scanner or something, but it yields a signal drop in the electrode vicinity if one looks at reconstructed images. So here you see, I'll make that bigger. Here you see a phantom scanned with electrodes next to it, and then you see, in terms of the image, you see this kind of mold here, here and here. The thing is, if this is happening in MR, then the electrodes are still a little bit away from where the thing of interest is, mainly the brain, because there's the scalp and the meninges and everything in between. So you also have a little bit of a dropout at the scalp, but this hardly touches the brain. So it's you don't get kind of strong cortical dropouts from the electrodes, but you get a little bit of dropout, which you can also use actually to do electrode localization, because then you have you get a picture of the scalp, of course, from the MR, and You also have, by means of the dropouts, you know where the electrodes were sitting, so you have fairly good localization of the electrodes on the scalp. There are also some methods that use that then for EEG source reconstruction. There seems to be a little bit of a radio frequency pulse perturbation, but in general, the artifacts in the MRI due to the EEG equipment seem to be negligible. So one can of course do all sorts of quality control also in case space and looking at the noise induced by having something additional in there. It seems to be by and large not a problem. So the problem is then only to correct for the MR artifacts in the EEG. And there are these two steps that are always done. One is gradient artifact removal, and the other one is ballistocardiogram removal. And the gradient artifact removal is actually quite straightforward, because the gradient artifact is, of course, due to a physical and programmed entity, namely the MR scanner and its sequence. So it's very constant over time and can be corrected by simply computing a template, so computing the average of the gradient artifact and then subtracting the artifact from the EEG. But this, of course, requires, because it's a high frequency induction process, requires a high EEG sampling rate. So this is how the idea. So one needs to synchronize nicely the clock of the MR scanner and the EEG system, so that you don't have because everything is of course in discrete time, that you kind of get these strange sample offsets, but that the clocks are running and the samples are always at the same time. Then you can register the onset of volume acquisition in the EEG, so you know when the onsets are, and then you can, like you do an ERP analysis, average all the gradients, or the local gradients if you want, and get a template, and then that represents the average gradient, and then subtract that again from each of these epochs. And then, of course, the idea is that what is left in addition to this average gradient is then likely the biologically induced activity. However, as you see here, if you do that, so if you do the gradient artifact correction, you still have in the EEG these fairly strong pulsation artifacts that are actually synchronized with the ECG, which you don't have in a normal EEG. I mean, your EEG that you looked at today didn't look like that. There might be some blinks, but you don't see the ECG. Essentially, it's not the ECG, as I will come to a second, but you don't see an ECG artifact usually in normal EEG, but you see it after when you do it with the EEG-fMRI. So that's then the second artifact, that's the ballistocardiogram artifact, and this is coming from movements of the leads and electrodes following cardiac pulsation. So that's not kind of a projection of the ECG, but it's because your heart is beating essentially, the whole thing is moving a little bit, and that needs to be also taken care of. And this, of course, is not synchronized with some technical device, but it's of biological origin. So it's a little bit harder to take care of and get away fully. So the one way to do that is, of course, to record the ECG and use this as an onset detection. One can also, it's a little bit like eye movements essentially in terms of the idea. So you can also directly detect the artifacts in the EEG. You don't necessarily need to have an EOG or an ECG, but one can. And then there are different, for example, ICA-like procedures that one can do to remove additional artifacts. So this is essentially how that looks. So here you have the EEG from the fMRI after gradient removal. We still have these kind of heartbeat synchronized artifacts, pulsation artifacts. And again, you would compute a template and then subtract that. And here you see that sometimes this then doesn't work that well. For example, here there seems to be some residual artifact at this point in time. But then, at least from on the naked eye, so if you look at this here, the EEG looks kind of like EEG that you would record outside. Yeah?
So why do we get this EEG from rapid blood EEG? Because if my heart also beats when I'm not in the fMRI.
Yes, but there's not a strong magnetic field around you that. Here the idea is that if you have a static magnetic field that is very strong, and you move now the wire, so you don't change the magnetic field, but you move the wire or the electrical conducting thing. So you move that a little bit. So this then again by induction creates a current, which is then creates these voltage deflections. Yeah, it's always induction, but here just movement of the wire. So essentially, if you would just do your normal EEG in a very strong magnetic field, then you will also see that. Good. So then the question is, when I worked on that, so Andy Baksha, with whom I worked, and a lot of these EEG-fMRI people, they are really interested in data quality and developing artifact correction methods and so on. And at least at that time. And then, of course, the question is how well does that work? Can one, if one looks at EEG recorded under normal conditions and EEG recorded under MR conditions, do the ERPs look roughly the same? I guess you looked at I assume you looked at the Ostwald 2010 paper where I think there are figures of. Are there figures of both? I'm not quite sure, but there are at least ERPs in there, and this should be the ERPs that were recorded inside the scanner. So yes, one can record ERPs. Here's another example, which is a little bit more fancy in the sense that there are more interesting, cognitively interesting effects. So this was a perceptual decision-making task where people needed to say whether the image is a face or a car, and they could either spatially attend it or not, and then these images were either of high coherence or low coherence. So if the coherence is high, then of course the task is easier, and the blue lines here with respect to P3A are a little bit lower. If it's harder, you get a stronger or a larger response, and you get that both if you just do the EEG as well as if you do the EEG together with the fMRI. Here it's a little bit smoother, the whole thing, due to the additional filtering effects of like gradient removal and BCG removal specifically. So that's kind of an effect that one still sees in the MRI environment, and also maybe not that strong, the amplification of the P100 by spatial attention, although this was a hard spatial attention task, so that was not attended against inhibited, but attended versus not attended. And this is still visible, at least on average, in the EEG from inside. So I didn't really expect that this kind of would hold up also these subtle effects. So the ERP is quite you still get it, might be a little bit of different amplitude and so on, but also these subtle effects, at least in these recordings, they show up. But you can see also, if you look at the topography, it looks, as Camilo would say, it looks quite noisy. So it's looks more noisy definitely than the original EEG. But what this means is essentially that one can record EEG event-related potentials okayish from the scanner. The story is a little bit different for frequency domain things, because one has to low-pass filter the data quite significantly, because there is all this high frequency power due to the gradient artifacts. So if you want to look at kind of induced or evoked power above, let's say, 30 hertz, maybe 40, with these standard ways of doing EEG-fMRI completely simultaneously, that will not work, because that needs to be filtered out, because that's really masked by residual high frequency artifacts from the gradients. So if you are interested in 80 hertz oscillations, that will be very tricky. But there is also work on trying to get up to 600 hertz or so. There is work that tries to actually establish methods that are still quite simultaneous, because you can of course also have gaps between gradient volume acquisitions and so on. And I think there's also this one paper by the group by Petra Ritter, where they have it really simultaneous and still can look at very high frequency. But definitely ERPs are easier than stuff above or in the gamma range, let's say. So if you're a gamma research scientist, then it will get tricky. Good. So these were these things in terms of data acquisition and the motivation. So do you want a break or do you want to go on? Who wants a break? Nobody. So we go on. So essentially there is some motivation to do EEG-fMRI also from a cognitive perspective, and one can do it technically, one can acquire the data, and one can also then have the data in a format that is kind of like the format or the type of quality that normal EEG and fMRI have, but then the question is what to do with the data. And as I said in the beginning, essentially this question is still open. It's a data analysis problem, it's a data fusion problem, it's a data modeling problem. So if one really wants to gain something from that, then one needs to think of how one analyzes the data. And another thing is, if one looks for correlation between EEG-fMRI, which some of these data integration methods do, then the question is also what one expects to hope, because if, let's say, whatever that means, you know that there are very different features in these domains, but if they would be fully correlated, so if EEG and fMRI correlate, then of course there again would not be much of a reason to do EEG-fMRI, because if they are 100% correlated, then you can basically compute the fMRI data from the EEG data. And so if you have a mere correlation that is not on induced by some latent source, but really in the signals themselves, then of course there wouldn't be a full motivation to do EEG-fMRI. I'm saying this because there was always a little bit of a hope that EEG and fMRI would be correlated, but whatever that means. But the question is, if your wish would be fulfilled, then essentially you could shut down MR facilities because you can just do EEG, or the other way around. But I I would advise the former because it's cheaper, it's safer. So, data integration. What do we want to talk about? So there is kind of a classical classification of EEG-fMRI data integration approaches that I will go over. So on the one hand, there are what one can call data-driven approaches. You know that I don't think that something like that exists, but they are just more data-driven in the sense that the models are fairly simple and boring, let's say. And in these data-driven approaches, one can distinguish asymmetric approaches, one being the integration through prediction using the GLM. So that's essentially doing fMRI analysis with some input from the EEG. One can do it asymmetric the other way around. One can do an EEG inverse solution, so do source reconstruction or dipole modeling with constraint based on the fMRI analysis. Then one can talk about data-driven approaches that are symmetric. Spatial-temporal independent component analysis, Tom Eichele calls this a symmetric method. I wouldn't call this a symmetric method. It's just symmetric because you do ICA in both domains. I would call my personal framework more symmetric. So that's the information theoretic framework, which has good motivations, but nobody uses it, and maybe nobody should use it. Then, opposed to the data-driven approaches, there are, of course, model-driven approaches, which pop up here and there, but aren't mainstream. I always hear again that the SPM people want to develop something like that. I heard it last time at the Christmas party here, but I think the main reason why this is not mentioned is because it's not an SPM, and if it's not an SPM or FSL, then nobody does it because it's too hard. The model-driven approaches would then be, of course, based on the inversion of biologically motivated forward models. So I will go over all of these, but not to the same detail. So let's look first at the data-driven approaches, and specifically the integration through prediction using the GLM, which is kind of the most common way to do EEG-fMRI data analysis. Of course, this is also kind of how things work already for epilepsy mapping. So this is from Stefan Deveners and Markus Ulzweger paper from 2007. So 2005, 2006, 2007, so shortly before my PhD, there seemed to be kind of that EEG-fMRI is actually happening in cognitive neuroscience. So there were a couple of papers that had some results on P3 and so on that suggested that this would become more kind of a common thing, but then it didn't happen. So there was work on EEG-fMRI by us, by also people in London, so Will Penny and Maria Marosa, they did some work, but it never really kind of made the mainstream, as one could have thought at that point. So what's happening here? The idea is one records simultaneous EEG-fMRI, then one removes the artifacts from the EEG, and this is somehow in this EEG-fMRI community, one does ICA. One has to do ICA. So I don't know why that is, but the EEG-fMRI people, they really love ICA, and you learned about ICA and how it can be used to do eye movement artifact correction. Of course, here one can, if one sees artifacts that are maybe high frequency and so on, one can also remove them. So, but it's not that EEG-fMRI data analysis only works with ICA. But if you look into papers from the EEG-fMRI GLM analysis kind of community, they will always have an ICA stable in there. Then the thing is, one and that's kind of a typical thing that one extracts parameters from the single trial. So you know that essentially when you do an ERP analysis, you average all trials. But of course, these trials were recorded over time, and at the same time, fMRI data was acquired. So the idea is here that you then, instead of averaging all the single trials in the EEG, you extract a certain feature. So, for example, the maximum over a certain time window where you think that for example, the P100 would be in, and then you observe this variability, so this trial-by-trial variability in these parameters, and you use these as regressors in a GLM analysis, so you combine them with the HF and get a regressor, and then you do a voxel-wise mass univariate fMRI data analysis. So essentially what you're doing here is, although it kind of goes this cognitive neuroscience, GLM, fMRI analysis way, you're correlating EEG single trial activity with fMRI single trial activity at each location in the brain, and then you can find regions in the brain that show such a correlation with a certain parameter and other regions that don't show such a correlation. And if your parameters are also then corresponding to specific time windows, you can say, okay, at 100 milliseconds there is a correlation with area A, and at 300 milliseconds there's a correlation with area Y, and then you kind of get this intuitive spatial temporal picture that this one area does something before the other area does, although that's not really what you do, you're just correlating things. So that's integration through prediction using the GLM. So essentially correlating EEG and fMRI data features.
So what's the feature that you extract from a single trial at the maximum amplitude?
For example, I mean, you can do whatever you want. So you can sort of, in our work, because with the information theory approach, we also extract features. You can use single trial amplitudes, you can use single trials areas under the curve, you can use single trial frequencies, so frequency powers. So if you do single trial alpha, single trial Fourier analysis, and then look at the frequency powers. So anything is open, and with some you will find something, and that's then your favorite feature. So the one thing that, in terms of the results that you get, in terms of checkerboards and event-related potentials and fMRI results, what you find there is that you find correlations across participants, but not within participants usually, which means that the trial-by-trial variability in EEG is not reflected in the fMRI. But if you correlate that over participants, meaning that people that have a strong ERP also have usually a stronger HRF response. So that is where you find correlations. I mean, it doesn't really tell you much about how the brain works or how visual processing works, but it tells you something that some people are good subjects and some people are bad subjects. I don't know, something like that. Also in terms of differences, let's say, between different contrast levels. So that's kind of the results that you get. And then the question is how you frame them. You can, of course, go and say, now this area responds at 100 milliseconds. You don't really have evidence for that, but your EEG feature that was extracted from 100 milliseconds seems to correlate in its trial-by-trial variability more with this area, and in another area more with a later component. But then you can, of course, say that if you want that this is then your spatial temporal signature. You can also do RSA on this and then say this is your spatial temporal signature. I mean, it's a correlation between trials. It's not a correlation in time. This is what needs to be clear. The other way around, this is just a pretty picture, essentially. you know that there are inverse solutions. So there are different ways to localize EEG activity. And you might remember that we talked about things biasing things towards surface things, or looking only at sources from the cortex, so looking only at dipoles distributed along the cortex from an anatomical image. Of course, one can, in a Bayesian framework, give some priors towards certain locations in the brain. And if one, for example, has an fMRI, a GLM result that says this area is strongly active, then one can, which is of course an average measure, so that's not really where you need simultaneous EEG-fMRI, but if you have simultaneous EEG-fMRI, it works as well. Then you can bias the source reconstruction toward this area, and you can do that. Then you have fMRI-informed EEG inverse solutions, which might be better in terms of their localizing power, as also shown in this example. So this is a simulation, so you have two sources, then simulated fMRI data, and then the source recovery as opposed to not fMRI weighted source recovery. Who can do it? I mean, it's a constraint like any constraint that you can also say for anatomical reasons. We think that our EEG activity, from functional and anatomical and previous literature, we think our EEG activity is primarily in the IPS. So we bias our source reconstruction towards the IPS. This is what you see, what you did with Felix. Just this. This has also very strong priors that actually get something that is kind of in the cortex and makes sense. So one can do this, and this would just be using an fMRI map essentially for that. This picture is just a picture and talks about the parallel independent component analysis framework by Tom Eichele. This only says do more ICA, so you do ICA on the EEG, then you also do, here, that's the EEG, on the fMRI, and then again you correlate the time courses that you get from the fMRI with the time, the single trial HRF convolved single trial parameters from the EEG. So if you think about what you know about ICA again is that, if you think about what you learned last term, that you have a time series, and then what you get are these weights and again time series. And of course, you can also do that to the data matrix that is fMRI. And then you get also kind of time series, which are independent components. So they are kind of, if you combine them, then they give you back your original signal, and maybe they are a little bit, so you can get rid of some stuff. And you correlate these here instead of correlating the original fMRI. But essentially, it's also a correlation with of EEG features with fMRI data.
So it's a correlation of the EEG-ICA components and the fMRI-ICA?
Essentially, yeah. Only that the fMRI ICs or the IC time courses, they remain like time courses. Like if you think about, you just do what you did for the EEG to fMRI data, you still get a time course. And for the EEG, you do the single trial quantification again. So you take from each IC, you have single trials, because again you have time courses in the EEG. You can split that up into single trials, and then you correlate when you do an HF step, because your fMRI time courses will still be at the temporal resolution of fMRI, because it's just the fMRI time, voxel time courses transformed, and then you do the correlation there.
So you would interpret that the same way as the first procedure that you explained?
Yeah, actually, with the problem, and that's also a good question, the problem with ICA that I have is that you cannot really interpret this, because there are these ICA people who do ICA on EEG, and then you get these independent components, and then you have to make some sense of it. This is kind of the thing that I always have with these data-driven things, because there's nothing in your model that tells you what this should mean besides the fact that these are independent, minimal Gaussian. So it's kind of technical constraints that have no biological or cognitive meaning whatsoever, and you just have a transformation of the data, and then you don't know actually what you should do. You can, of course, then write a story and say, okay, this looks like that, like that, and so you do the modeling part essentially in the end. That's while in a real model or in a more sensible way, you would think first, so these are my intuitions, then I formalize them, and then I test them whether they kind of conform with the data. And you actually put more effort into the model. So this is why I'm not a big ICA fan. Or RSA or PCA or whatever. Yo. Other questions? No. Then maybe briefly about what I did in my PhD, because this also came up recently again, these pictures. I think in terms of new frameworks by Birte Vossmann and Turner and so on doing something. So it's not as outdated as I tend to think. So what my motivation was to look at EEG-fMRI was the following. First, I realized that they always talk about EEG-fMRI correlations, and I was confused because there is, of course, there's also the stimulus, and some of the stimulus didn't seem to play a role, so this was confusing. Then I wanted to learn about more probability theory and information theory, so that seemed to make sense. And then, of course, looking at correlation, not in terms of correlations, which are linear models, but in terms of nonlinear models as reflected by mutual information, was kind of a motivation too, because the idea was that maybe when we only look at these correlations in a linear framework, maybe we are missing something. So that was the overall motivation, also because there's also, I read kind of papers that use very similar approaches for invasive neural data analysis, and so I could see some parallels between this and what we want to do with EEG-fMRI, and then I just said, let's just take this framework and apply it here and see what happens. I got a PhD. That's what happened. Else, I don't know. Don't think much happened. So the whole thing starts from the idea that there's variance in signals, and when I mean EEG and fMRI, these are now always single trial features. Yeah? So that you somehow decompose EEG and fMRI into single trials, and then there might be covariation between EEG stuff and the stimulus. There might be something with fMRI and the stimulus. You all know that this is the case because you looked at these kind of situations in your fMRI data analysis. Then, in addition to that, that is stimulus-induced correlation between EEG and fMRI, and also stimulus-related covariation between EEG and fMRI, which is here. There is, or might also be, stimulus-unrelated covariation between EEG and fMRI, right? So because in terms of resting state covariation, so that because there's neural activity, EEG signals might go up at the same time that fMRI signals go up, because then they are driven by this latent thing called neural activity. So what then essentially the work of my PhD and the second part of the paper that I told you essentially not to read did was to formalize this picture, which was also from this or from another Debner paper, in terms of a probability distribution and essentially conditional EEG and fMRI distribution conditions on the stimulus. And then quantify things in this, oops, sorry, someone got stuck. Hello? Yeah, quantify this using information theoretic quantities. So essentially first to look at the overall joint probability distribution of these things and then quantify them using information theoretic concepts. So which information theoretic concepts? On the one hand, entropy, which is a measure of variance. So this is actually discrete entropy, so which is the real entropy. There's also something called differential entropy, which is not the real entropy, and it's actually shown here. Now that's very subtle, so if you're really interested in different forms of entropy, look into the variational-based paper with Ludger into the supplement, because there we go all the way about these things. So entropy is a measure that can be applied to probability distributions and measures how variable the random variable is that is reflected in this probability distribution. So this is shown here for a Gaussian. So here you see Gaussians of different variance. Higher variance for the Gaussian means higher entropy. Yeah, so there's a little formula that one can use to convert the variance parameter of a Gaussian to entropy. You can look it up on Wikipedia. It derives from solving the integral for the Gaussian probability density function. Then there's something called Kullback-Leibler divergence or cross entropy, which is a measure of the distance between two probability distributions. Again, one can kind of nicely discuss that for two Gaussians. So here there are two Gaussians which are essentially the same. Maybe let's make this bigger. Which are essentially the same, and then the KL divergence between those two is smallest. So that's here. So this is with respect to, there's always the second with respect to the first Gaussian that you see here. Then one can, if one shifts the means, you see that the KL divergence goes up quite a lot. So this is shifting this mean and then measuring the KL divergence with respect to this. And then you get up here. It also changes if you increase the variance, but not as much. So this is the variance. So the KL divergence is a very important measure in probabilistic modeling because it's a good measure to compare probability distributions and measures the distance between them. So if they look differently, and the KL divergence is larger than if they look the same. And finally, and this was the central measure that we then used for evaluating all this, there's what is called mutual information. And mutual information is the KL divergence between a joint distribution and its factorized analog. Yeah? So the question is, so you know what joint distributions are, and you know that factorized distributions model independence. So if two random variables are independent, then, so if there's no stochastic relationship between variable x and variable y, then this is described as the unique thing that is factorization. So that's this. And all other forms of covariations can be captured in the joint distribution. Yeah? So the joint distribution does not always need to encode a linear correlation. It can be anything. It's basically anything that is not independence is kind of a joint distribution that is not independent. And the idea is then to actually compare in mutual information the joint distribution of two random variables to the distribution that you can create artificially by factorizing the distribution, so creating a joint distribution by multiplying the marginal distributions. Because if you have measured the joint distribution, you can always, of course, integrate out over one variable and get the marginal distributions and use them to create a factorized joint distribution. So what does that mean, maybe more in a more applied sense? So this shows the difference between correlation and mutual information for different modeling scenarios. So here you see one variable x, and you see that y data that are sampled here, conditional on each of these x values, don't show much of a pattern, as you see. And in this case, both mutual information and correlation are quite low. Then you have the case where you have a linear dependency of y on x. So if x goes up, the values that you sample for y also go up. In this case, you see mutual information and correlation both going up. So that's the C case. And then this is the nonlinear case. You have kind of this inverted square function here. So if x is really small, then y goes up, and if x is really large, then y goes up. And this cannot be detected by correlation, because correlation wants to fit a straight line to that, but it can be detected by mutual information, as you see here. So that's kind of the nonlinear motivation, nonlinear relationship motivation for looking at mutual information. Thing is, in real data, you of course never have these kind of things, but you have something like this or this. So whether you use mutual information or correlation, I don't think it makes much of a difference. So then basically we just defined all these mutual information quantities that relate to the variance aspects that we were interested in. So the information in the EEG about the stimulus, the information in the fMRI about the stimulus, so SSCO is the stimulus, and these are just the forms for the mutual information. Then the question of multimodal stimulus-related information. So can we predict the stimulus better if we look at both EEG and fMRI as opposed to looking only at one of them? And then the question of intermodal information, so the correlation between EEG-fMRI, essentially both in a what is called activity dependence and conditionability dependence, which is at a fixed stimulus. All of those, what you see here, you can also do with correlation. So it's not a feature of information theory that you can look at things like activity dependence and conditional dependence. That's just something that was addressed in these earlier papers of looking at these things with respect to neurophysiology. And we explicitly looked at them, and we looked at them explicitly using mutual information. But you can look at activity dependence or conditional dependence, so correlation, conditional on a stimulus, also with correlation, not only with mutual information. So then we basically cover these things in a formal setting. So we have stimulus-related information from both the EEG and the fMRI. Oops, hello. So there and there. We can look at the stimulus-related shared variance and the stimulus-unrelated shared variance. And we can look at the whole thing in terms of the information about the stimulus from EEG-fMRI. It's not really in there, but it's close. And of course, this is also interesting in terms of synergy, so that whether you actually gain something. How does one do such an analysis in practice? So first, one needs to specify what one means by EEG and by fMRI. And as I said earlier, this is by means of single trial feature selection. So in this case, for a high contrast stimulus and a low contrast stimulus, we extracted the P100 amplitude and the HF maximum. Then you can plot them. But of course, that's one feature. There can be many more features. Then, if one wants to compute mutual information, one needs the probability mass functions. So one has to do some kind of estimation of these probability mass functions. for example, by histogram is shown here, or kernel density estimation is not shown here. Then one can evaluate the information in theoretic quantities, and then it's a data-driven method. You have some result and you have to make some sense of it. So after my PhD, I decided I want to do model-based approach and not data-driven approaches, because in the end you end up with something like this, and you have to make some sense of it. So this was from the paper that you know. So it's not too surprising what you see here. It's kind of more a confirmation of the method, essentially. There is information in the P100 about the stimulus. What does that mean? That means that the P100 discriminates between high and low contrast stimulus. I mean, this is of course already, you know that from here, but yeah, at least it shows up again. Amplitude, latency, and area under the curve essentially from fMRI also are informative about the stimulus, as you see here already. And if you use both of them, you also have information about the stimulus. And there the question is more, does looking at both of them buy you anything as compared to looking just at the sum of the information of this and this through some magic? And the basic finding is no, not really. And then we also looked at the correlation between EEG and fMRI, both in a non-stimulus conditional manner and in a stimulus conditional manner. And that was interesting because for a little bit of some time I couldn't really explain what's going on here. So there seems to be covariation conditional on a stimulus and not if you look at it independent of stimulus. And if one wants to understand this, one has to think a little bit again of what's actually happening here. So it helps if one simulates stuff. So here what I simulated is a negative correlation between EEG and fMRI conditional on one stimulus, and a positive correlation conditional on the other stimulus. Yeah? So let's make this a little bit larger because this is the key here. So you see if the things are red, that's single trials from one stimulus. You see a positive correlation. If things are blue, single trials from the other stimulus, you have a negative correlation. Now, if you look at the overall correlation between the marginals, so EEG and fMRI, because these are kind of overlaid, you don't really get much of a correlation or information here. But conditional on one stimulus and conditional on the other stimulus, of course, there is quite some mutual information and also, in this case, correlation, because you can already see that here from the data. Now, if you average this conditional over stimuli, of course, this remains high. And this just shows that you can achieve essentially the same thing with, not quite, no, that's also not quite with correlation. No, essentially you can do it with correlation. Sorry, forget what I said. I think what we are picking up here is a little bit that there's still some nonlinear dependence, of course, also here, which you don't see in the pure correlation, but the basic effect that you have positive and negative correlation. Well, here it then also, if here it then averages, if you average it, it gets out. So it's a little bit, I don't want to oversell that mutual information is better than correlation, because in general it isn't, but it has a little bit of value also in this kind of simulation. Now, if one makes this more noisy, then of course that gets, the pattern gets weaker, but it's still there. These are simulations. The question is, how did the actual real data that we analyzed here, because this is what I said in the first hour of the winter term, data analysis is always data reduction. So here we reduced the data quite significantly. How does the data look that actually is underlying these plots? And with some imagination, one might see that the blue ones are a little bit more spread out in this, along this axis, and the red ones are a little bit more split out along this axis, so that if you look stimulus conditional, you have correlation or mutual information. And if you look over the average, so if you forget about the color, then you might not have this, so which explains these results. Of course, if one would not do this analysis and just look at this like this, one could also say that. Good. We also use this method to characterize the human perceptual decision-making system, and we created these great spatial temporal information maps. It's awesome. It's in the +1 paper. Look at it. It's great. So, finally, model-based approaches. So these were data-driven approaches. So the prediction one, which is kind of a correlative approach, it doesn't, what the GLM prediction thing, what I always find a little bit weird in that is that you really have to think carefully about stimulus-induced effects, because there you really have to think how you set up the GLM, whether you look at covariation that is going beyond stimulus-induced effects or not. That really just depends on your GLM setup. This gets a little bit clearer if you look at conditional things like with the mutual information, or you can of course also do that with conditional correlation. But again, you look at correlations between stimuli and EEG and fMRI features, and then you know that there are these correlations. In what one really wants to do, I think always, is to inform neuroscientific, maybe even neurocognitive theory by brain imaging data. And this, of course, only works if you have an underlying model that generates your data and somehow has a means to combine them in a sensible way. So the basic model is relatively clear, so one would think that there is some underlying hidden neural activity, in this case, this from Pedro Valdez-Sousa, an ensemble of postsynaptic potentials which gets transformed both to the EEG and the MEG, and somehow this latent thing you want to recover from both EEG and BOLD, and in a way that somehow is awesome. Frameworks for this, of course, get more involved, especially if you want to do it over time. So one thing that they propose and that we also work with for some time are state space models or random differential equations, which look like this. So you have a latent thing and you model its change at a given time point by a function of itself, some parameters and some random process, and you have an observation model that maps this onto data. And then if one spells that out in more detail, this is how they do it. So you have the EPSP going into a vasodilatory feed-forward signal and going directly into the EEG. So the EPSP goes on in one stream, it goes into the BOLD, and the other stream it goes directly to the EEG. So you have this latent quantity, and then you can, if you invert it properly, you can infer the time course of the EPSP. It hasn't really happened though. This is kind of the thing, or at least it has not been shown that this really helps with anything. So something that I've been pondering over the last 6 years that I didn't work on EEG-fMRI always is if you want better spatial temporal localization, you need a model that explicitly accounts for spatial and temporal aspects. And this model is a partial differential equation model. So if you, without partial differential equation models, or at least motivated by partial differential equation models, you will never get anywhere. Partial differential equation models, however, are quite computationally demanding. So I think, and I also worked a little bit in this direction, in delay differential equations, because they explicitly here the change in one area is affected only after some time by some other area. So the distance, so there's a spatial dimension that specifically influences the temporal domain. So this is kind of a sensible groundwork model. The question is how to, and this is just work that I haven't done, and no one has done. The question is, if one has kind of identified a model where space and time interact, then the question is how to invert this and what it actually means. And so I worked a little bit in this direction, but this is all not published and not even in a proposal. Worked to taking more the stance that it's not so much that EEG and fMRI have high temporal resolution and each complementary, but that we believe the temporal resolution of the EEG more than we believe the temporal resolution of the fMRI. So what I mean by that is, if you think about being able to sample bold a little bit higher than the usual TR, so let's say at a, 200 milliseconds, 100 milliseconds approach, then you have high temporal resolution fMRI. So essentially that's what you want. But somehow, because you have this delay of up to 6 seconds, you might still not really, if you have a kind of a very short 100 milliseconds shift of the bold response, the question is whether you believe that. Another problem is, of course, that in fMRI you usually cannot really say much about the location and time for 1 second or so. So you have a uniform probability that something happened in that time. Thing is, if you believe that fMRI is very precise in time, then it doesn't matter that things happening only 6 seconds later. If there's happening at 6.01 second, then as opposed to 6.00 seconds, then you still have a fairly high temporal resolution. And the same thing, talking about space for the EEG. The question is whether you believe these reconstructions. And if one then basically encodes this belief in terms of the spatial and the temporal resolution, in terms of these variances, then by Bayesian sensor fusion, one can actually gain better localization, also from a classical perspective. So these are ideas that may make more or less sense to you right now. But that's kind of my current state, and I actually haven't worked on this for 1.5 years or something now, because there's all this other stuff to finish. But in the end, I think it's only these kind of approaches, so that you have models that actually need space and time information, and models that make explicit what you actually want to gain, like this, that will help with EEG-fMRI integration, and then specifically also binding EEG and fMRI models, neural models, to cognitive computational models. So there's a lot of modeling work to do. It requires good modeling skills, so good mathematics, good programming skills, and then it's all awesome and it all works. Good. So this is the end. So just as a summary, intuitively, there's this complementary spatial and temporal resolution, and this has this premise of high spatial temporal resolution imaging. If you look at data acquisition, that's easily done. Artifacts can be used, and artifacts can be removed easily. There exists many data integration methods, so there's always every 3 or 4 years there's a new review on how things can be combined. But from my perspective, what is really the aim is not clear, and in the end also whether a model-driven approach, in which sense this yields high spatial temporal resolution, is also not clear. There is a little bit of a problem in terms of EEG-fMRI, that a lot of people that work on the data quality aspects of EEG-fMRI and more the data acquisition and so on, they don't like models. So they are like, no, we don't want to do models. So this is why nothing happens there. And then, of course, people who do models and inference can also do other stuff. There was now a paper by your friend here, Deco. Have you seen Deco's new paper in Neuron? That is also a fusion paper, but he there fuses PET, diffusion, fMRI, and DTI, also using a latent neural mass model. It's kind of, it's in a way the typical Deco approach, so the fitting and the stuff is really basic, but at least it's using the same kind of basic approach that you need an underlying model to fuse different stuff, so you cannot do it without modeling. So information theory does not help, ICA does not help, GLM, fMRI does not help. You need to develop models. You need to be a scientist and not a data analysis SPM GUI clicking monkey. Now that's a general point. Good. Questions?
So you talked about mutual information versus correlations that might not be that much more useful. I thought it was quite interesting. So why would you? Like it looked like it was independent of like the correlation of your data was.
Yeah, the thing is, that's definitely the case. The thing is that if you think about Taylor approximations, so all relationships, if you think about two things that are related, so there's a function that maps x into y. All of these relations are locally linear. So if you go zoom in, then it will always be linear. And then my feeling is that with the stuff that we are measuring, on the one hand, I mean, there are dynamic ranges of things that we are looking at in the fMRI and the EEG, and somehow in these dynamic ranges that we are looking at, things are linear. That's kind of, so this is my impression, so that what we haven't done is really, which should have been done, but of course then my PhD was over, do a really quantitative comparison, whether any of these features, if one looks at correlation, nothing happens, and if one looks at mutual information, something happens, and then really sort through and figure out whether one can see some non-linearities. The thing is, with non-linearities, they are also not that easy to spot visually, let's say, because anything can be that. It's just a non-independence, and of course, visually one sees linear relationships quite well. So, yeah. So my feeling, just from the results that we have in these studies, which I then also compared with results that are known from the literature, which all use linear methods, seem to be that if there was something linear, we picked it up, but we didn't really pick up much more, or at least it wasn't apparent to me. But yeah, if somebody feels inclined to look into that again, it can be done. But I think actually it's more interesting to build the relationships already into your data analysis method by thinking about them and then comparing different relationships that also have meaning to you, because mutual information then says, okay, there's covariation, things are not independent, but it doesn't say more. I mean, it might say it's quite strong covariation or quite little covariation, but it doesn't come with a mechanistic picture of how the function from x to y actually looks. So if you have a square, then you see high mutual information, but if you have high mutual information, doesn't mean that there's a square or something else. But so this is why it's kind of a screening test for maybe nonlinearities if one compares it with correlations, but beyond that, it doesn't really yield a mechanistic picture. Anything else?
So do you know anyone who's actively working on this still?
Model-based approaches? Or
Yeah, that's EEG-fMRI integration.
I'm working on it. Well, I mean, there are EEG-fMRI labs which do nothing but EEG-fMRI, but they are usually looking more into methods development. So, for example, people around Matt Brooks, so in Nottingham, and in Birmingham, Carl Millinger, and so on, they're doing stuff. Then you have the occasional modeling people who do that and go through that phase. So there was some stuff at Phil with Will Penny, but he's not doing that currently. And then you have actually a lot of people that acquire EEG-fMRI data. I'm just reviewing a paper, just started reviewing that today, which reports on the results of an EEG study. That's what the abstract and the intro say. And then suddenly they talk about MRI acquisition, and I was a little bit confused. So they acquired EEG-fMRI data. We also, in the clinics, they acquire EEG-fMRI data. I actually review EEG-fMRI data papers quite often. Thing is, they then have the EEG-fMRI data, but don't either only look at the fMRI and the EEG data, like in this paper, or they do some prediction analysis. But that's also unlikely. So I think a lot of people have these setups now sitting around. They wrote a grant proposal at one point, I don't know, in 2012 for some psychology thingy, DFG gremium, where they said, we will acquire EEG-fMRI data. We use this and this with this, and we will use this approach, Debenar 2007, and then they get the money, and they acquired the data. It's good, it's all there. But then once the data is acquired and cleaned, what do you do? And then it's actually harder to make a coherent story out of an EEG-fMRI analysis than of an EEG analysis only, or an fMRI analysis only, because there are certain conventions that people think, okay, this is an EEG study, that is done well, and then you get it published. So, and of course, another reason why then EEG-fMRI data is seldomly analyzed in the end is because it's not an SPM. So if you could click your EEG-fMRI data analysis and for some time get some great papers from it, then people would do it. Of course, they would not get the great papers anymore because it's not novel anymore, but they still would get papers. And now it's just, it's basically due to the fact that there are hardly any good computational cognitive neuroscience labs in the world.
That's interesting because it's surprisingly unproblematic.
It's completely
unproblematic.
unproblematic.
The computer science lecture, and Peter Quick, your professor, said it doesn't make sense to use fMRI EEG because you combine the disadvantages and not advantages. And I basically forgot about it, but yeah, it doesn't make any sense to do it. But
yeah, I mean, this is also what people say, but this is also, if you want to say you combine the advantages and disadvantages, but the crucial thing, it's a data fusion problem, and this is the thing. You need to be explicit of what you actually want to get, and this you can only get from formalizing that. So this is typical sensor fusion, where you have a sensor that one sensor is good in one domain and the other sensor is good in the other domain, which you in principle have in EEG-fMRI. And if you can say that, then you can build this in your forward model, and then it's and this is what this shows, and also this shows, is you actually gain something. So you gain precision in terms of recovering. So maybe I can tell you the details here. So this is EPSP in space and time. So this is space-time, one dimension of space, one dimension of time. This is where the real neural activity, so the EPSP, happened. Yeah? So that's the black one. then the idea is that there is some variability of how such a thing is mapped onto an EEG signal or an fMRI signal. This is shown here. So this is the true but unknown thing. And then if you sample an EEG signal from that, that will be shifted in space. It will never change much in time, but it will be shifted in space. The fMRI, that's maybe the more tricky assumption, is that will never be much shifted in space, but there's uncertainty in time. And this is what I meant by, is there really uncertainty in time? There's definitely uncertainty in time in the MRI because of the low sampling. Because if you just have one data point per 1 second, you cannot say when in this 1 second. You can just say in this 1 second. So you have these, if you make this commitment, and this is a modeling commitment, and then people say, yeah, but I don't want to make commitments in modeling. I want to click around in my GUI and get my result. So if you make this modeling commitment and can be explicit about it, and then people will write, oh, but you have a model. You can have another model. What about that other model? Then you can say, yeah, we could have another software. Anyway, so if you build this into your thing and then sample, in fact, this is what is shown here. So here you have then measurements that were acquired. And if you then look at, and this is what this shows, if you look at conditional on the measurement, look at where the EEG puts your postsynaptic potential, you have mislocalization in space. If you look where the fMRI puts the thing, you have mislocalization in time. If you look at the combined version, you're much closer to the true thing. And this is very much motivated from a Bayesian approach. So this shows the same thing if you motivate the same thing from a frequency perspective. So sensor fusion does exist. So it's not that it doesn't exist or doesn't mathematically work. It's just that translating these sensor fusion. So first of all, people usually don't know sensor fusion that exists and that it works. And that you can gain something if this is good in one area and this is other thing is good in the other area, but it needs these commitments. And then the other thing is, of course, that this shows these things for essentially two-dimensional vectors and Gaussian distributions, which are, of course, mathematically and also computationally quite easy to handle. But of course, what it misses is a lot of neurophysiological detail that one also will want to build in. And I've worked a little bit in this direction based on this, and then, of course, you get into problems of convolution and inverting convolution, because in general, convolution is not invertible. And so on. So it just requires work and commitment and but mainly technical knowledge. So in principle, the intuition that you gain something from combining them is true. But to have it in a way that you actually like it and feel like that this is really capturing EEG and fMRI in its biological and maybe even cognitive complexity, that work has not been done. And I wish somebody would do that, so I want to be scooped on this, because that would be something reasonable. But people don't do it because of how academia works. Maybe if I stick around longer, currently I'm not working on this, but I will come back to it if I'm allowed to stay around longer. Good. Any other questions? No. Good. Then we almost did 2 hours. And then, yeah, I don't know. See you maybe at your master defense, because I don't think, or some people in a second at the EEG, thing, but the rest of you, I think I will not see again until the Master Defense if I'm an external examiner, which I haven't heard much about. Otherwise, I will not, I don't think I will take part unless Felix or Hauke get sick in your workshop. So have fun in your master thesis. Goodbye.